It was one of the world's most ambitious engineering projects. A massive hydroelectric dam generating more kilowatts than any other on the planet. To build it, the path of a mighty South American river was blocked. Thousands of acres of precious wild animal habitat and tens of thousands of homes disappeared in a huge flood. 40,000 workers battled against the forces of nature, rocketing temperatures, the constant threat of killer floods. Behind it all, the potential for catastrophe. Building the Itaipu Dam took 7 tough years. This giant quest for energy came only at a devastating price. The Rio Parana. At 4,000 kilometers long, it's South America's second biggest river, outstripped only by the mighty Amazon. For part of its course, the Parana marks the border between Brazil and Paraguay. Here, the river's path is barred by a man-made structure, the Itaipu Dam. It's the world's most powerful hydroelectric dam. It pumps out 90,000 gigawatts every year, enough to power London for over 3 years. It took an army of 40,000 workers and some £13.5 billion to build this monstrous structure. Italy's Piero Sembinelli was one of the dam's key engineers.
Possibly we didn't realize how difficult the project was going to be.
It stands in one of the remotest corners of the world. So why build the most ambitious and powerful dam on the planet here? Rewind to the 1960s, a boom time for Brazil. Its economy was growing by 10% a year, but the population was growing too. Already standing at over 70 million, forecasters predicted a rise to 170 million in just 3 decades, making Brazil one of the world's most densely populated countries. Brazil's growth created a spiraling demand for energy. The government had to find a way to satisfy the power-hungry masses of the future, or face economic crisis. But how? The country didn't have enough oil and gas to head off an energy crisis, and it couldn't afford to spend big money on fuel imports. But then, someone had a brainwave. Why not use a natural asset that's free and that Brazil has plenty of? Water. A staggering 10% of all the fresh water in the world is found in Brazil. Its 40,000 kilometers of rivers could reach right around the globe. If the vast potential of water could be harnessed by hydroelectric technology, energy demands could be met without costly fuel imports. Brazil was thinking big. The government wanted one massive dam to supply a huge chunk of the nation's energy demands. Finding the perfect site for such a big dam wasn't easy. The river had to hold a volume of water great enough to produce the energy needed. It must flow through narrow banks, and its bedrock had to be strong enough to take the massive weight of the dam walls. This was the obvious spot. The River Iguaçu feeds one of the biggest waterfalls in Brazil, but it only had 1/8 of the water needed for the monster dam. One by one, engineers checked out 50 other sites. None made the grade. Finally, the perfect location was found. The River Parana is the 7th largest in the world, holding 4 times as much water as America's Colorado River. At a spot called Itaipu, it flows through a deep underwater gorge. Geological surveys revealed that the bedrock was strong enough to bear the dam's enormous weight. Itaipu seemed perfect, but there was a huge obstacle. The gorge sits right on the border between Brazil and its old enemy, Paraguay. In the 19th century, the two countries had fought in a bitter war. Paraguay lost half its territory and half its population was killed. Even over 100 years later, there was still mistrust between the two peoples. 1966, complex negotiations began between the two countries. For 7 years, the dam project hung in the balance. But in the end, the lure of vast supplies of energy proved irresistible. On the 26th of April 1973, Brazil and Paraguay signed a treaty. The Itaipu Dam got the green light. Itaipu looked set to outstrip some of the world's greatest dam projects. It was destined to be 18 times as long as the mighty Hoover Dam, and 9 times as heavy. Most importantly, it would produce 6 times more electricity. But building the world's most powerful hydro dam meant making sacrifices. A vast area of farmland and forest would need to be flooded to feed the monster dam. Tens of thousands of people stood to lose their homes, and the habitats of thousands of animal species would disappear forever. As the Itaipu project reached the point of no return. May 1975. Old enemies Brazil and Paraguay signed an historic pact, which enabled construction to begin on the biggest hydro dam in the world. The aim, to harness the power of the mighty Parana River. The goal, an energy bonanza for both countries. The multi-billion-pound budget was jointly funded by the Brazilian government and by foreign investors. Engineers found a site on the river that seemed perfect for the dam. But to build it, they would first need to divert the Parana from the course it had flowed for thousands of years and reroute it. A massive diversion channel had to be carved through the rock of the riverbank to temporarily divert the river away from the dam construction site. At 2 kilometers long and 80 meters deep, it was the biggest diversion channel ever attempted. If it failed to divert the river correctly, the whole project would be doomed. Piero Sambinelli was the engineer in charge of building the channel.
It was a mighty struggle that we fought. The Paraná was the most difficult diversion ever tried.
Second of May 1975. Building the Itaipu Dam began. First job, to dig the channel diverting the river. It took 3 years of explosives, mechanical diggers, and sheer brute force to slice through the rock. The dig threw up a mounting pile of waste rock known as spoil. As the months passed, the unwanted earth and rock reached the size of Rio's famous Sugarloaf Mountain. Meanwhile, others were counting the environmental cost of such a big dam. Once complete, the Itaipu Dam would turn the Parana River Valley into a giant reservoir, flooding an area twice the size of the American city of Chicago to a depth of 100 meters. One reason this valley has been chosen was because of its sparse population. But there was still 600 square kilometers of agricultural land and thousands of small farms on the Brazilian side, and on the Paraguayan bank, 470 square kilometers of rainforest, home to thousands of wild animal species. The thirst for energy comes at a price. As the dig got underway, environmental consultants were drafted in. Their task, to assess the wild animals and plants saved from the coming flood. It was the first dam project to attempt a major rescue plan, but at this stage there were only 17 people involved, mostly volunteers. Brazilian Fernão Carbonar was one of the team.
It was the beginning of the environmental movement all around the world, but regulations weren't as strict and legal requirements as tough as they are today.
It was a race against the clock. If the rescue wasn't completed before the valley was flooded, thousands of animals would perish, and any endangered species living here could be put at risk. The work was time-consuming.
Angico vermelho, 24.8.
The survey basically consisted of walking through the woods and sighting the animals, looking for their foot tracks.
But people lived here too, some 40,000 of them. Whole villages and small farms, some of them home to families for generations, would be lost forever beneath the floodwater. Those affected had to be compensated, but the authorities needed to know how much to pay out. And that meant embarking on one of the world's biggest ever real estate valuations. First, the whole area was photographed from the air, but that didn't give enough information to calculate compensation. To get more detail, the valuers had to send an army of photographers on foot to scour every square metre of the Parana Valley. These men and women were on a mission. They had to get an accurate valuation of every home and its surrounding land. Everything was recorded and photographed. Alberto Fres valued hundreds of homes.
The houses were measured, described, and photographed one by one. And all belongings, even if it was just a stool, it was photographed.
While the valuation process was seeming to take forever, the digging of the diversion channel was right on schedule. 3 years after digging began, engineers were now set to demolish the channel's concrete seals and send the Great Parana River pouring down the channel. 8 a.m. on October the 20th, 1978. Dynamite charges are set at each end of the channel. It's a tense moment. If the explosion damages the channel, it could set the project back years.
It was a fantastic moment, incredible moment. The blast was like a firework.
The mighty Parana is thundering down its new course. It's a momentous achievement. The Itaipu engineers have altered the path of one of South America's biggest rivers. But this was only phase 1 of the diversion. Some water still flowed down the old riverbed. So huge temporary dams called cofferdams were built to force all the water down the diversion channel, away from the dam construction site. They were made by dumping huge pieces of rock into the river until the flow was stopped. The cofferdams might only be temporary, but British engineer Bill Beath knows how secure they had to be.
Cofferdams prevent the river from flowing into the area where the dam is being built.
Should these collapse during construction,
it would be a total disaster.
Brazil has some of the most torrential rainfall in the world, and rising water could put the cofferdams under pressure or even burst the walls. That would bring a devastating wall of water down on hundreds of workers. The engineers hoped that they would have enough warning of rising river levels to safely evacuate workers. Until the main dam walls were built, all that stood between the workers and the threat of flood was a wall of rubble. With the River Parana now fully diverted, the biggest job of all, building the huge walls of the Itaipu Dam, finally began. But there was a problem. A hydroelectric dam works by dropping water onto turbines, making them turn at great speed to create electricity. The taller the dam, the greater the drop, and the more power is produced. Itaipu's engineers knew that the water in the dam must fall a full 100 meters to produce the promised record-breaking amounts of power. Yet, the riverbed is only 50 meters deep. The solution? Build a series of secondary dams. These raised the height of the concrete central dam to make it tall enough to do the job. But it meant running the dam structure right across the valley for 7 kilometers. Autumn 1975. Work began on the secondary dams.
Meanwhile,
the valuation of the houses, farms and land in the river valley which the dam will flood has also been completed. Brazilian and Paraguayan authorities have learned that before they submerge the area under 100 meters of water, they must buy up 8,500 homes and farms. The cost? £250 million in today's money. That's on top of the multi-billion-pound price tag for the dam itself. Offers of compensation were rushed out. Most were accepted, but a handful of people did mount legal challenges. But engineers were more worried about keeping the secondary dams on schedule. They desperately needed more workers, an army of them. Yet the Parana Valley was sparsely populated and remote. Its only town, Foz do Iguaçu, was a small frontier settlement. The nearest big city, Sao Paulo, was 1,000 kilometers away. Project managers had to choreograph a massive migration of workers into the area. They bussed in tens of thousands of workers from all over Brazil. Everything a large town needs, from schools and hospitals to churches and kindergartens, had to be built. New housing estates were built just for dam workers. Massive catering production lines were set up to feed the ever-increasing number of workers. The town of Foz do Iguaçu began growing at an incredible rate.
We're really talking about moving into a one-horse town with something like 30,000 workers.
What was once a tiny backwater became a gold rush town, practically overnight. While the new gangs of workers tackled the secondary dams, the engineers were wrestling with the design for the vast main dam that must block the river at its deepest point. All dams must be capable of one thing. They must resist the unimaginably vast pressure of the water in the reservoir behind them. Where geography allows, dams can be simple walls anchored to the surrounding rock. But Itaipu has no such help from the terrain. It must stand alone. So Itaipu followed a design that relied solely on its own weight. Engineers called this a gravity dam. The idea was to make the structure so heavy the water simply couldn't move it. To work, the dam had to weigh 61 million tons. But a dam is only as good as its foundation. The bedrock must be incredibly strong. Any weaknesses could cause the dam to collapse, an unthinkable disaster. The engineers undertook a detailed survey. The results were good. The dam's foundations were sound. And the engineers also had a money-saving trick up their sleeve. A dam made out of solid concrete would weigh more than it needs to and add huge costs. So they planned instead to make the main dam walls hollow.
As long as it has enough weight, it will resist the water pressure. That does not mean that it has to be absolutely solid. It can be hollow and still resist the water pressure.
Building the dam hollow meant its base could be made even wider with the same amount of concrete, and the walls would slope more gently, pushing the water pressure down to the base where the dam is strongest. It also meant the power-generating equipment could be housed inside the dam itself. It was a clever solution. Meanwhile, the environmental team completed their survey of wildlife in the area to be flooded. They found 129 species of birds, 32 species of mammal, and 9 species of reptile. Now they needed to work out how many animals they could trap and remove, and where they could be safely relocated. June 1979. Preparation for the main dam was well underway. The managers were determined to stay on schedule. Everything was going smoothly. But then the work came to an abrupt standstill. There was a problem with the bedrock.
As we dug into the foundations, we discovered, in fact, that the conditions weren't exactly what we had expected.
It was disastrous news. The survey gave the bedrock a clean bill of health, but now engineers had come across a weak layer of crumbling rock, like a rotten tooth 20 meters down. The engineers feared that it wouldn't support the weight of the dam. If they carried on building, the dam would collapse. Tunnels were dug down through the rock so that engineers could investigate the suspect layer. Only a thorough underground inspection would reveal the scale of the problem. They prayed it was just one bad pocket of rock. Engineer Corrado Piacentini probed the secrets of the bedrock.
This is the good rock, and this is the jointed weak rock. As you can see, it's very soft and not good for a foundation.
The crumbling rock stretched right through the dam's planned foundations. Building an 11 million ton dam on top of this would have been criminally irresponsible. Workers stood idle while engineers and geologists wrestled with the problem. Finally, they hatched a plan that might just work. They couldn't build on the crumbling rock layer, but could they replace it? Like demonic dentists, the engineers drilled out the decaying rock and gave it a massive filling, with extra strong concrete. It did the trick, but the extra work took months and added a further £10 million to the budget. Fixing the crumbling rock layer threatened to delay the whole dam building schedule. And the relentless heat of the Brazilian sun was about to give the engineers another headache. May 1982. The 40,000 workers building the Itaipu Dam in the heart of South America have grappled with a potentially catastrophic problem. Fractured bedrock beneath the foundations threatened the massively heavy structure with collapse. At stake, the supply of energy to Brazil's future generations. Engineers came up with a solution. It seemed to be working. Like a bad tooth, the rotten rock layer beneath the Itaipu Dam site was drilled and filled with extra strong concrete, so that it could take the weight of the dam. At the same time, work on the dam's giant central walls continued. The construction team set about casting 18 massive concrete blocks. Each block had to be made separately. Huge steel structures were erected to receive the concrete and hold it in place until set. But it wasn't just the scale of the job that posed a challenge for the engineers. If they poured this amount of concrete the usual way, it just wouldn't set properly. When concrete sets, the cement reacts with water, creating heat. In smaller concrete blocks, the core temperature cools and sets relatively quickly. But in large blocks, the core temperature stays high longer. And as the surface cools and sets at a faster rate than the core, hundreds of cracks can appear, fatally weakening the concrete. And that wasn't the only problem. Temperatures in Brazil can easily soar past 40 degrees centigrade. If the huge blocks were allowed to set in the sun, they could reach more than 90 degrees. This too would cause weak spots and cracks. Engineers conducted test after test on concrete set in these conditions to see how it reacted to extreme pressure. Even good concrete has a breaking point. Concrete dried by the sun would be much weaker. A solution had to be found. After wrestling with the concrete problem, engineers finally came up with the answer: refrigeration on an unprecedented scale. 2 huge cooling plants were used to chill every gram of concrete. Engineer Adalberto Chenu recalls the scene.
The stone was washed with icy water and blasted with cold air. Using a large number of ice chips, we were able to produce concrete with a mean temperature of just 4 degrees. And because we had an efficient transportation system, the concrete only reached 7 degrees by the time we were pouring it into the molds.
The scale of the refrigeration job was vast. The 2 plants had the cooling capacity of over 50,000 domestic freezers. By June 1982, the race was on to meet the dam's completion date, just 3 months away. Overhead cableways were now feeding the dam's insatiable hunger for concrete in a continual round of supply and demand.
This cement was being trucked in over thousands of kilometers. At one time, something like about 1 40-ton truck every 20 minutes cement.
40,000 people were working at a rate equivalent to raising a 20-story building every 55 minutes. As the project neared 0 hour, the pace became increasingly fierce. Adalberto Chenu ran the work schedule.
During construction, we had really tight deadlines. We worked in 2 shifts of 12 hours for almost 360 days a year.
The work went on around the clock. Right through the night, men and machines moved about the huge construction site in a finely tuned ballet. As the countdown to the dam's completion and the valley flooding began, conservationists went into action. They hoped to save 30,000 animals, relocating them to new areas or to wildlife sanctuaries. The rescue team knew that it was a race against time to save as many animals as possible before the flood. At the same time, the massive task of relocating over 8,500 families got underway. Compensation claims were settled in lengthy negotiations and court cases. Some were given money, others were given a similar property and land elsewhere. Some of these families had lived and farmed in the Parana Valley for generations. For many, it was a devastating moment as they left their homes forever. The countdown continued. The 7-kilometer string of dams was now complete. Itaipu was about to take its place as one of the longest and most impressive dam structures in the world. But the next step was absolutely critical. Engineers have to close off the channel that diverts the Parana River. The river will then slowly flood the entire valley. creating the vast reservoir that will feed the dam and drive its power-generating turbines. Once filled, the water pressure in the Itaipu Dam's reservoir will be like 4,000 bulldozers pushing ceaselessly against the dam walls. The engineers had made highly detailed calculations and were confident that the massive walls were more than strong enough to hold back the water. But the filling of any dam reservoir is a critical moment. The concrete dam walls are all that stand between the vast reservoir and the people of Foz do Iguaçu. What if the dam were to fail?
The failure of any major dam is always a major disaster, because the amounts of water that would be freed would create a wave that would flow down the river and create tremendous damage.
If the walls of Itaipu were to fail, the escaping wave of water would dwarf all but the most extreme flash floods Brazil has ever seen. A city-sized body of water would charge down the Parana Valley. The wave could reach 50 kilometers an hour and demolish all in its path but the most substantial buildings. The death toll would depend on whether people living in the valley had any warning of the impending flood. June the 3rd, 1976. The Teton Dam in Idaho, USA, was being filled for the first time. Engineers spotted a crack in the walls and tried to repair it. They failed. 2 days later, the western third of the dam simply disintegrated. $1 in damage to property. Miraculously, only 14 people died. But the incident was a timely reminder of the dangers of dam construction. October 1982. 7 years since building began, the big day had arrived. The massive sluice gates in the diversion channel were closed. The River Parana flowed once again down its original course. It poured over the cofferdams. It charged into the reservoir. Whatever happened, there was no way to stop the water now. As the water rose, more and more pressure was put on the huge concrete walls. The reservoir took 14 days to fill to its final depth of 100 meters. Everyone had been evacuated from the flood area, but some stayed to watch their homes disappear under the rising water. And an army of over 300 conservationists from Brazil and Paraguay set out on one last mission to save as many animals as possible from drowning. As the water levels slowly rose, small islands of high land were left behind. They're only temporary, and after a few hours they would disappear forever beneath the surface. For now, they provided a last desperate refuge for terrified animals. Like modern-day Noahs in tiny arks, Fernão Carbonar and his rescue team tried to save as many as they could before it was too late.
We used some nets, we used some hooks for the snakes, and some of them we just caught them by the tails.
Soon the animals had only treetops to cling to above the rising water. And there were hazards for the rescue team too.
The water was high, so you can imagine yourself going by boat on a treetop. You didn't really know what to expect to find between the leaves. Sometimes you just look to your right, and about 20, 30 centimeters you had a rattlesnake or some other kind of poisonous animal.
But apart from the odd scratch and bite, the rescuers managed to avoid serious injury. For days, the rescue progressed and the floodwaters continued to rise. Within 2 weeks, a vast stretch of the Parana Valley was lost forever. Itaipu's reservoir now stretched as far as the eye could see. The dam's giant walls were holding back the water, but the engineers now had to stop it rising any further. If the water flowed over the top of the dam, the walls could be weakened and even start to crack, with potentially catastrophic consequences. Engineers had a trick up their sleeve. A crucial escape chute called a spillway had been built at the edge of the dam.
It's like a giant version of the overflow of your bathtub. When the water gets too high, it drains away, without causing a flood. The big difference is, this overflow must cope with 64 million litres of water per second. If it's been wrongly designed, the force of the water could damage it, setting the project back years. But there can be no rehearsals. The first time the spillway is used will be for real. October 1982. Excited crowds and world media gather to watch the big event. Engineers prepare to lift the sluice gates and open the spillway for the first time. The water begins as a trickle. It soon becomes a raging torrent. It's working. The spillway is taking the strain. It's controlling a cascade of water 22 times bigger than Niagara Falls. Brazil is now home to the biggest man-made waterfall on the planet.
Engineer Adalberto Chenu witnessed the moment.
It was a really unforgettable spectacle, and it will remain engraved on my memory forever.
The engineers were relieved and elated for the moment, but their spillway worries weren't over yet. They feared that the volume of water thundering off the spillway might in some way damage the dam itself.
At the Furnas lab in Rio de Janeiro, Roberto de Souza builds detailed high-tech models of dams to analyze the consequences of even the smallest miscalculation in spillway design.
With this scale model of a dam spillway, we're carrying out an extremely detailed study of the effects of the water as it falls, of the energy that it can produce, energy that may damage the structure itself.
When water crashes off the end of the spillway, it lands below the dam with great force, churning up the river. This energy must be dissipated using an upward curve like a ski jump that forces the water up into the air, reducing its force.
The energy dissipation is so important that you could say a good design of spillway can avoid damage to both the actual structure and the land downstream.
Engineers relied on scale models to get the angle of the ski jump just right. If it's wrong, the water will turn back on itself and could seriously erode the riverbank. And if the process continued over years, it could eat away at the foundations of the dam. Itaipu's engineers have calculated that there will be some erosion, but not enough to do any serious damage. All they can do for now is keep checking the riverbank and hope. If they've got it wrong, the structure of the dam itself could be in peril.
The vast reservoir feeding the Itaipu Dam has been filled, flooding thousands of square kilometers of agricultural land and rainforest. 30,000 assorted birds, mammals and reptiles were saved from drowning by conservationists. But they all needed new homes. Some were relocated, but 300 rescued animals were found a new home in a wildlife sanctuary. 700 square kilometers of forest also disappeared in the valley flooding. To replace the lost trees, millions of new saplings were planted around the reservoir's edge. A conservation program like this looks basic by modern standards, but in the 80s it represented a trailblazing bid to minimize the damage caused by large-scale dams. Over the next 9 years, Itaipu's final frenetic stage unfolded. With the dam walls finished, work began on the power-generating plant. "18 giant tubes to funnel water to the turbines went up. The turbines themselves weigh 800 tons. They're so huge that special vehicles had to be built to transport them. And that wasn't all. The bulk of the Itaipu Dam's electricity was destined for the huge cities of Sao Paulo and Rio de Janeiro, over 1,000 kilometers away. A massive network of pylons stretching right across the Brazilian countryside was erected. The electric power lines from the dam are long enough to stretch around the globe 1.5 times. As the dam neared the moment of producing power, engineers nervously inspected the riverbank for signs of damage from water thundering down the spillway.
This is the kind of erosion that huge volumes of water can do when traveling at high speed.
How serious was the erosion caused by the spillway? It didn't look good. The engineers took precise measurements. They made further calculations. Was the erosion creeping ever closer to the dam's foundations? To their great relief, the engineers found their original predictions were right. The erosion was not getting any worse.
This shows how important it is to get the design of the spillway exactly right.
The foundations of the dam were safe. Itaipu was now nearing completion. The pace had been unrelenting. But South America's biggest ever engineering project had come at great human cost. Records aren't precise, but 145 people are thought to have lost their lives in accidents while building Itaipu. May 1984, and Itaipu was about to fulfill its purpose and produce its first electricity. It was the moment everyone had been waiting for, the culmination of 9 years of grueling work. Water poured through the gates at the top of the dam, thundered down and turned the turbines. One by one, further turbines were brought online, and in April 1991, Itaipu became the most powerful hydroelectric plant on the planet. Itaipu was now feeding the energy demands of 24 million Brazilians in Rio de Janeiro and Sao Paulo. The electricity flowed without a hitch for 10 years.
Until January the 21st, 2002, 1:30 p.m. Without any warning, 13 of Itaipu's 18 giant turbines suddenly grind to a halt. Electricity production stops. The engineers at Itaipu are mystified. What has gone wrong? Rio and Sao Paulo are brought to a standstill. Traffic lights stop working, causing 30-mile backups. Subway systems close down. People are trapped in elevators. Offices, homes, factories are plunged into darkness. What is causing this cataclysmic power failure? José Ricardo de Silveira was in charge of power output.
All the generators and all the transmission systems for Brazil suddenly cut out. At the time, we didn't know exactly what was going on.
After frantic investigations, electricians finally tracked the problem down. a power line had collapsed. The transmission system couldn't cope with the power level that Itaipu was generating. It had tripped the switch that turns off the mighty dam's generating system. An inquiry followed. The result? £8 billion were poured into upgrading the transmission system to prevent future blackouts. In one afternoon, Brazil's urban population saw just how much they relied on Itaipu's electricity.
20 years on, the Itaipu Dam remains an extraordinary achievement and was recently voted one of the 7 wonders of the modern world by engineers. Today, a staggering 90% of Brazil's energy is generated by hydroelectric dams. Dams like this have helped Brazilian cities and industries to grow and brought electricity to people in remote areas of the country. But the heavy reliance on water power has come at a price. And all around the world, there's a growing awareness of the environmental havoc that hydroelectric dams can cause. At Itaipu, dead treetops serve as a powerful reminder of a valley that has gone forever, and the enormous price Brazilians have paid in their quest for power.